Hey-oh, who all do we have here? Let's see who's in the chat. We'll wake up Mewbot. We're going to start some activity here in a moment, but we'll get Mewbot awake. There we go. Re-clicking through. Got to wake him back up. Nicole, good to see you here. Kayla, good to see you here. We're going to do Shreya, good to see you. Everybody's here. Everybody. 100 points out there. Let's do 500 points. We're going to start up some activity here in just half a second. So get ready in the chat for activity on Logistic. So let's jump in here and do it. So here's the activity file. I should have just downloaded it. Let's go ahead and click to download. We got the Act 11 account data. And here we are opening it, and there we are. So with the activity file open, we are going to do some logistic probability curves. And so with this, great job, Kayla, you have 500,000 points. That is awesome, reaching Stat Nation hamster tier level. Awesome. That's from mini-term, winter mini-term. So with this right here, let's take a look. Using the data command line to load in the data frame junk, the data contains the late 1990s when junk mail filters were being designed. The goal is to predict the probability that an email is junk or safe from the junk column in the data frame. Words, frequencies like money, buy, free, your, meeting, symbols, frequencies like brackets, parentheses, hashtags, and how many words are capitalized. The last three columns in the data set contain information on how many times in a row all capital letters appear. How well does the logistic model work as a junk mail filter? Note, safe comes last alphabetically. So the model will be predicting the probability of an email being safe. Well, that's nice that they added that on right there. So what happens if you type in junk right here and it doesn't show up? Who knows why junk wouldn't show up for some people, which you might be typing it in and it doesn't show up right now. You're like, hey, wait a minute, it's not showing up. And I want you to see what it says after it, which is very important. So why would someone type in junk? And I'm going to hit enter and it's going to capitalize it for me. And that'll load in the junk data set right there. Why would that not show up for somebody? Why would someone say, hey, it's Brian, yours works, but mine doesn't, which is a common question. So why would that not work? Exactly. Great job right there. Another 100 points right there. Great answer. Because if you notice as you type junk, it tells, or at least mine does, it says it's in reg class right there, which is the library it's contained in. Not that it's a good, Drea, so good answers, Shreya, good answers. It's that junk is contained within the reg class library. And so this is a kind of like preloaded in data set. It's not necessarily in our files. This is like within the reg class library. Yeah, exactly. And so it's within the library of reg class, which there's other libraries, which like FPP3, which you don't have, you could get if you want, which is forecasting practices and principles. If you load that up, then you could go over here and load data, OS, and you see how these have FPP3 on them. So these are things right here. Oh, yeah. And on assignments, a lot of times we might have the wrong directory. And for this right here, I can now load my FPP3 data sets right there, which you won't be using those, but just seeing the extension lets you know that's what it's doing. So we got the junk data set loaded in. The naive model, we were just covering that moments ago, predicts every mail to be the majority level. Run summary when which level of junk or safe is the majority level. What is the misclassification of the naive? And this is such a great test question right here. So let's go ahead and put a timestamp right here and put question 1. So we got 5 minutes in. Question 1. So we need to go in here and go to summary and run it on the junk data set and run it on junk. Now make sure it is lowercase junk except for the capital J. Now, what do you notice about this? Most emails, and this was the late 90s before things got out of control, most emails are what? Most emails are what right here? Most emails are what? Just look at it and say, from all the emails, from the 4,601 emails, most of them are this. Safe. So if you got a random email, you'd probably assume, if I had to have you bet money on it, now don't worry, but if you had to bet, you'd probably bet the email's safe. Why? Because the majority of them are safe. So what we can actually do is we can do the math for us, and we can figure out what percent it is. Now, if you notice, I'm just taking the values and timesing them by, or dividing them by how many observations there are. So when we do this right here, we can actually get the probability based on the naive level, or the naive model, which is going to predict all emails are safe. So what percent of the time would the naive model be wrong? Because the naive model is going to say, everything's safe. All email, that one's safe, that one's safe, that one's safe, 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 safe. The naive model will be wrong on 1,813 emails, and it'd be wrong on what percent? About 40, right? 39.4%. So it'd be wrong this percentage of the time right here. It would predict those are safe because it just says everything's safe. The naive model says all emails are safe because most are safe. So since the naive model says, yep, good work right there, Kayla, excellent catch, it's going to say every single email we get is safe because most are safe. So it would get wrong every junk email, which is 39.4% of the emails. And that's really great review of what we were just doing. A particular strong association exists between the probability of being junk and free, everything free. Now, an important thing to know is we're predicting the probability that the email is junk or it's junk mail. So when we store this model, we have to do GLM. That stands for the generalized linear model. It has with it the argument family. We still have y tilde x comma data equals. But family, which is set to default Gaussian, needs to be binomial for 2 levels. Binomial. Gaussian is actually the normal curve. We could use this for linear. It creates a problem with some of our code, so we don't use that for linear. So we're going to go here and predict junk. Make sure it's just junk, not the one it's trying to autocomplete, because that's the data frame. That's the variable inside the data frame. And the variable of interest is free. So we're going to go right here and write free. And then we're going to do data equals, and this is the capital junk because that's the data frame. And then family equals binomial. There we go. Well, that's fine. It's telling me a warning because it's logistic. It's saying, hey, did you know I used some 0-1 probabilities? And I say, well, that's what I wanted you to do. Warnings are fine. It's just trying to alert you to things. No big deal. Hey, Adam, so good to see you and excellent work. So I've been doing a lot on like GitHub and stuff. Keep it up, Adam. Excellent work. 100 points right there for Adam. Now, when you take a look at this, probably the visual is going to be the biggest help for this. The visualization of this model is really going to help us clue in on what's going on right here. Think about if you have an email that says like free this, free that. The probability of it being safe is going to be what? Frankly, if it says safe, free one time, the probability of it being safe is going to go what? The more times it says something about something being free in it. The probability of it being safe is doing what? It goes down, right? Exactly. It's going to go lower probabilities. It's going to be unlikely that it's safe. That means that the coefficient in this output will be what? So finish my sentence. The coefficient in this output will be what? So when we see the coefficient, you can almost see it. The coefficient, because the probability is decreasing the more times it says free, like 2 emails is going to be negative, right? There it is right there. So 2 emails where we get 2 different emails, but one says free more than the other. The email that says free is less likely to be safe, i.e. lower probability. So 2 emails where one email says free more than the other, the email that says free more often is less likely to be safe. You can basically say emails that say free more often are less likely to be safe. Kind of works for this. It's a lot simpler to interpret these coefficients. Do remember when we interpret, we only interpret the sign. Too much free is sus right there. I agree right there. Too much free is sus, and that's the problem. Frankly, I think actually if it says free more than once or one or more times, that 50-50 breakpoint is at 0.4. So if it even says free, it's probably junk. It's more likely junk than not. So if it says free one time, it's like, no, don't open that email. It said free somewhere in that email, so don't open it. But how well does this model do? When we look at this model right here, we need to go to the confusion matrix on it. The confusion matrix will give us the predictions. Now, the model will make right and wrong predictions. Like I said, when we were ending class, I was like, this activity will really hone in on what we're doing. Okay. Where's the important email you missed from your mom? Which are all important emails. Where's that in this? If you know how to read this, tell me where the important emails that you didn't open from your mom were. In what number are the important emails? I'll explain how to read in a moment. So if you're walking through this with us, the 127, oh, great job. I think you got it. Because the 127 are emails we predicted are junk, but the emails were actually safe. So these were emails predicted junk, and we should probably use a different color right here because we would say that we what these emails, think something missed something. These emails right here that were predicted junk, so we think, I think that's a junk email, but it's actually a safe email. It's totally fine. It was our mom emailing us saying, hey, I found some free food. And we're like, junk. So those are what classified, we would say. Those are what classified. How would we say? We say, oh, we something classified those emails. What terminology would we use? Misclassified. Great job, Nicole. Great job, Kayla. We misclassified. Where else is a misclassification? Where else is does this not line up? What other emails are misclassified? When this is where we are like, we read an email, it's like, I need your help with this. And we're like, sure. Oh, no, viruses. Oh, no, viruses. Oh, we got all the viruses. Great job, Lillian. Where did we get all the viruses? What number here represents us getting all those viruses? Great job, Shreya and Nicole right there, where it is actually junk, but we predicted it's safe. You know what's interesting? We were talking about type 1 and type 2 error. So if the null hypothesis is that the email is safe till you have evidence it's junk, like you need evidence that it's a junk mail, a type 1 error is when the null is true. Oh my gosh. Type 1 error, the null is true. Good. I even got to check sometimes myself. And then we reject it. So a type 1 error, if the null is true, it's actually safe, and we reject it. This would be the type 1 error, and this would be a type 2 error where it's actually, let me see here. So in the type 2 error, oh my God, wait. I think I've got it reversed. In a type, no, I think I have it right now. In a type 1 error, the null is true, so it has to actually be safe. There we go. And in the type 2 error, the null is false, but we fail to reject the null. There we go. So that actually comes into play right here. If you think about, we're trying to find evidence that it's junk. So we actually have the type 1 and type 2 error here, because in a type 1, the null is true. It's actually safe. And thus we would make an error by predicting it's junk. So that's an error because it's actually safe. So we made an error. Type 1 is that it's safe, but we reject it. Exact Kayla, 500 points, doing the example right here before I can. Great work. And so we don't want to make these errors. These are misclassifications right here. And it relates back to 201. So we always try to connect those ideas with things we've been learning. And sometimes Brian has to review in his head too. But why do we like these values? These are values that we like, and why? Why do we like that 638? Why do we like that 2661 right there? Why do we like those values? Why are we like, hey, those are good values? Because we correctly classified them. We correctly predicted them. We said, I bet that's a junk email. Oh, it is a junk email. I bet that's a safe email. And those 261 that we said, I think that's safe, they were actually safe. Nice job. Good job with dinner right there. But you know what's also interesting, and I do want to point this out, is because what can you always do from this table? And a lot of people don't realize this, and we do put test questions like this. From this table, you could actually calculate something we did earlier. What can you calculate from this model, from this table over here? And look, most emails are actually safe. The naive. Great job, Shreya. Great practice from class. The majority level. So here, you can actually figure out the amount you would classify according to the naive. And this is the naive over here. The naive model only knows what things actually are. So when you only look at the actuals of this table, you can actually do the naive and say, well, most emails are safe. I guess they're all safe. So how many would the naive model get wrong again? Looking at this right here, how many would the naive model get wrong? Remember, most emails are safe, so I guess they're all safe. And this is the naive model, which doesn't use the predictions from our model. It would get wrong 1831. And that's just good practice of looking at the table and realizing, oh, most emails are safe. So it would get wrong the junk because it would say, well, I guess they're all safe. And it would get right 60%. So the naive model gets correct 60%. And the amount the naive model gets correct will always be what to 50%. So good check right here, Lillian, is that the amount the naive model gets correct will always be what to 50%. The amount it gets correct will always be what to 50%. Because think it predicts the majority level, it'll always be higher than. Does that make sense? So if you get something like 60% saying it gets 60% wrong, then check the complement, because it gets 60% right, it would get 40% wrong. So whatever the amount of the majority level is, which is basically 60%, it would get the other 40% wrong. So it's a good check right there. And great work, Lillian, 100 points, great practice. And this is the actual model. Your model This is the model where the X's are making prediction. And then this over here can be used for the naive. You still use it with your model, but if you only focus in on that, you're focusing in on just the naive. So once again, we do write test questions where you really don't want to look at that. If it's just talking about the naive, you focus in on this. You do still have to use this value when you're doing your total model, though, to find out things like misclassification rate. Let's ask that. What is the misclassification rate of this model right now? What is the misclassification rate? Very famous. I'm trying to throw you as many test questions as I can. If you're watching this, this is a really good review for the test right now. What is the misclassification rate of this model, which is the percent it misclassifies? So we've got it kind of marked on where the errors are at. What is the misclassification rate? I think Shreya doing an amazing job right there. Another 100 points, Shreya. Well, the naive might have a 40% misclassification rate. So now we're talking about our actual model. So if it says the naive, it would be 40%. For our model, we need to take where the errors are at, which is the 127 plus 117. And we'll always say the naive if we're saying like the misclassification rate of the naive. So the model itself is considered this, but there's always the idea of the naive, which is when you don't use any X's. And people are telling me, got a lot of confirmation there. So very quickly in your head, what is the accuracy of the naive? And you can round it. If that's the misclassification of the naive, and great work, Lillian. What is 100 points? Lillian doing some great math right there. Just use this version and tell me what is the accuracy of the naive, just looking at it that way. Which then you could do, add up the yellow numbers to get the accuracy, but use that and just be like, oh, if that's the misclassification, my accuracy would be this. What would be the accuracy of my model? And really good practice. 70, I think 72, right? So 72, you can figure it out exactly if you want. I'll write the exact mathematics. No worries. The exact mathematics for the accuracy are going to be 638. So always, the reason I like to do a lot of estimating is if you estimate it and your answer is close, you've done a good job. So great job, Lillian, throwing the extra decimal. Great work right there. There we go. And so, yeah, no, it's always good to do a quick estimate in your head and then check calculator. But do use calculator because you'll watch, if you watch many office hours, I'll do it in my head and I'll get it wrong. Be like, oh, I just can't do math today. So the double check is very good to like make sure you're doing your work properly. If you do it in your head and you get the same on the calculator, then you probably did it right. If they're incongruent, maybe you got it right on the calculator, maybe you got it right in your head. But it's always a good double check. I did 12 plus and nice. So let's see what the questions are asking here. And there's a lot of good practice. Emails that contain a higher fraction of the word free have a higher probability of being junk. Now be careful. This is true or false. It's worded a little bit interestingly. Remember, this is probability of safe. So emails that say free more often have a higher probability of being junk. True or false? What do you think? Emails that say free more often have a higher probability of being junk. That is, it's very true because they have a lower probability of being safe. So the complement of safe is junk. So this is very, very true right here. We can do like a star around it. Makes it bold for the moment. There we go. How many junk emails were correctly classified? The junk emails that were correctly classified would be these right here. They were predicted junk and they were correctly classified right here. So that's how many were correctly classified. How many safe emails? So we're just going to this column right here. I'll try to write here this column. Great job, Lillian. Good practice. How many safe emails were incorrectly classified as junk? Right here. So these are the ones that... Wait. Oh, yeah. Well, no. Oh, Brian's getting it wrong. So these are the ones that are actually safe. These are actually safe. So how many were misclassified? I think Shreya got it because Brian was on the wrong spot. How many safe emails? So they're actually safe. Does that make sense? These are the ones, when we're saying actually, we're saying it is a safe email. That's what actually means, is that the email is actually safe. So how many safe emails, so we're looking at only the safe emails, were incorrectly classified, i.e. predicted to be junk? I guess so, right, Shreya? So here is the ones that were predicted to be drunk that were actually safe. We did the misclassification rate of the model. And the misclassification rate of the model, let's go to document 44, is going to be right here, the 127 plus 1,175. Oh, right there. So that would be, so Shreya, I think you have the classification rate. So the misclassification rate is this one, and the classification rate is this one, or the accuracy. Does that make sense, Shreya, right there? Oh, I'm sorry, Kayla. The misclassification is here by the pink numbers, and the classification is the accuracy right here. So the misclassification is about 28%, and then the accuracy is about 71.7%. Mm-hmm. And so when it says misclassification, that's the ones it gets wrong, i.e. the off diagonal. So these would be the off diagonal here, the ones that are not on the diagonal. Check the validity of the simple regression by running associate and check regression. Both of them? Sure, okay. Does the logistic curve provide a reasonable reflection of reality and how the probability... So, we've never done associate on the test. If it insists. Y tilde x comma data equals. Here we go. Oh, it's all mad. See why they asked me to do that. I don't see. Can't do it. Wouldn't be prudent. So what am I doing? Save my regression. I won't do that. Check regression. And we were talking about this at the end of class too. Look at the whoa. Thoughts on this. There's some thoughts to be had on this. Good or bad? Good or bad? Uh-oh. What do we got going on here? We got two friends, and they're in strong agreement about this. Yeah, what did mine say something too? Don't worry, we don't put that on the test. Oh, be careful. It's something about the associate. I don't think we have to run associate, so I might just... I don't know why it's getting mad. So is this good? What is the null hypothesis when we run check regression? So we ran check regression right here, and we're looking at the model assumptions. And anytime we do model assumptions, we assume that everything's okay. This is very bad. This is very, very bad. And don't worry, 100 points right there, good practice. When we look at p-values just mean, do we have statistically significant results? And since the p-value is low right here, we reject the null. Well, what was the null hypothesis? Well, but in this instance, Lillian, so it's all subjective. Because for this test, anytime we run check regression, the easiest way to remember the conditions for check regression is everything is what? Like the null hypothesis would be everything is what? So if you ever run check regression on any model, any output you get for check regression is that your conditions are what? The null hypothesis would be your conditions are what? Not that they're true, that everything's good. So the null hypothesis would be everything's good. Does that make sense? So tell me, what would you do right here with your belief that the conditions are good? And this is when running check regression, i.e. that the logistic curve is a good fit, which is what we're talking about. So what would you do to your belief that the logistic curve is a good fit? You would say, I'm going to what that belief? I'd reject that. Now, do remember, it doesn't always mean rejecting null is good or bad. It's situational. The null in this instance is that the logistic curve is a good fit, and you're throwing out that idea. So that means the curve we fit back here behind me, what do you think about that? That was a bad idea. Like, maybe we shouldn't fit it. It's not a good reflection of reality. Like, it doesn't model the data well. If you were to talk about baking a cake, and to figure out the probability of somebody liking the cake, fit a logistic curve, your logistic curve would have to have a what shape? The logistic curve has to have a what shape? I know this isn't baking a cake, but the logistic curve would have a what shape if you predicted the probability of somebody liking the cake with how long the cake was cooked. It'd have to have this S shape. So if you try to fit the logistic curve to that data, Do you think the logistic curve would fit well if we look at how long it takes to bake a cake and the probability of somebody liking it? Do you think if you try to fit an S to this data, it would fit well? Do you think there's some way I could draw an S that would somehow fit to where, there's probably a right time to cook a cake? If you think about, the probability of somebody liking a cake is in this region. So I'd say no. So if you ran the check regression right here, the p-value would come back very, very what? Low or high. Remember, it assumes that the logistic curve is a good idea till evidence elsewise. So if you ran a check regression right here, it would assume the logistic curve is a good idea, and your p-value would come back very, 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 very what? And it would actually fit this sort of curve because it has a trouble time fitting it, which would not fit the data well. The p-value on the check regression would come back very what? Low. So high if good, right? But high if good, but this curve right here, which is an S, a very bad S, is a good or bad idea right now. Putting an S on this is a good or bad idea. Like if I put an S to this, is that a good idea? Like, should I try to fit an S to that data? So yes or no to this. Should I be trying to fit an S right here? That's a bad idea, right? I shouldn't do that. So when the p-value comes back this, it's informing me when I'm checking the regression that this was a bad idea, that the condition is not met, that this curve is not a reasonable reflection of reality. Remember, we think everything's A-okay till we have evidence it's bad. Does that make sense for what this is telling us in the check regression? The null hypothesis is everything is good. So you could literally write, S is good, and you could write like the S idea, the sigmoidal curve is a bad idea. And it's just telling you, should you be doing this? It's checking the idea of doing it. We're not looking at the significance of the curve or the variables in the curve. We're just saying, should we even be doing this? And it's telling me, should I be doing this? Yes or no? So what is this output telling me right here? Should I be doing this curve over here? What is it telling me? It says, Brian, you should or should not be doing this. Remember, we're rejecting the null that it's a good idea. So is it telling me, yes, you should do this, or no, you should not? It's saying no. It's saying I reject that this is a good idea. Low p-value, reject the null that it's a good idea. Remember, the null is that the S is a good idea, and the alternative is that it's a bad idea. It's saying I have evidence that you shouldn't be doing this. So when you do the check regression, remember, you're checking conditions, and low p-values are bad because that means there's a violation of the condition. It's evidence of a problem. All check regression outputs, every time you run this command right here, low p-values are what? And I know that's counterintuitive because we usually think, oh, it's statistically significant. Every time you run check regression, because you assume conditions are good, low p-values would be what for your conditions that you're assuming are true? They're bad. Does that make sense? It's a twist of reality, but in this instance, we are assuming things are good. So low p-values are like, it's a bad thing right there. So do remember that check regression output, we don't want to see low p-values because now we have problems. This is a bad idea. So good review right there. Good review of check regression. Even when using the logistic curve does not provide a reasonable description, it's saying right there, oh, you found some low p-values. The description of how it changes. Oh no, Shreya, I'm sorry. The model may still be more useful than the naive in the sense that it makes accurate predictions. Does the simple logistic model get more predictions correct than the naive model? So remember earlier, we did calculate the probability of the naive being accurate. Our model right here, our model gets right. Let's add them up. This is the on diagonal. We're adding up the on diagonal, the ones that it predicts junk that are junk, the ones that predict safe that are safe. And we would add those. So our model gets that percent correct. And going back here to where we did the naive model can be calculated right here. Rather, we can figure out the accuracy of the naive from this table, as we say we should. I mean, just explain to me briefly, like, oh, it does about this much better. Just look at it numerically. Our model does this. That's the top number. And the naive does this. So maybe, how would you talk to someone about that? Say, yeah, it does about this. How would you just say, oh, yeah, I mean, our model gets this. The other model gets this. That's a difference of this. So, what would you think? Remember, we're just talking about numbers. Just sometimes the stats is, I think just how we generally talk, say, well, yeah, the model gets about this right, and the no knowledge model gets about this right. So it does about this percent better. What do you think? I'd say maybe it could be useful. You never know. It's a little useful. It's a little bit. Just a little bit. Our model gets 71% right. The naive model gets 60% right. So there's a difference about 11%. So, 10-ish, 11-ish, 10-ish, a little more than 10%. It's all right. That's right. Now fit the full model. Ooh. To fit the full model here, we're going to take save into, we're going to hit the right buttons on the computer. We're going to save into LM, the GLM, junk tilde dot data equals junk email family equals binomial. There we go. And we got all the data. Let's look at the summary. It's going to be ridiculous. That's pretty crazy. It looks like it found some stuff right here. So, wow. That's a lot of variables. A lot of variables. We cannot plot this anymore, so no more graphics for us on this. Let's go here to the check regression. Do we like the check regression? Yes or no? Do you like this? Yes or no? What are your thoughts? Do you like that? No. Still bad. But when I run the confusion matrix, no, I agree. It's pretty bad. This is telling me yuck, how my model makes predictions. And actually, wow. Okay, good. Actually, wow, this is pretty cool. How many, so you can add them up for me. How many does this new model get wrong? The model's still super problematic with its reflection of reality. But how many total does this get wrong? So if you get used to seeing the confusion matrix output, you can be like, oh, well, it gets this many wrong. So remember, we're looking at the off diagonal now, things where it's predicted safe, actually junk, things where it's predicted junk, actually safe. You want the things that don't connect, that are incongruent right here, the off diagonal. The on diagonal is the one that lines up predicted safe, predicted junk, actual junk, as in predicted safe, actually safe, lines up, predicted junk, actually junk. How many does this get wrong? How many does it get wrong? It might be, Shreya, great work right there. Another 100 points. I think Shreya might have the right answer. That seems close. That seems like you maybe calculated, and that would be the percent. That's known as the misclassification rate. Great job, Shreya. Another 100 points. Yep, and Lillian's showing how to add them up. And so what could you get from this pretty quickly? Think of the A word for this, not accept. We don't say that here. So there's the misclassification rate. This is sometimes called the classification rate, also known as another A word for it, known as the blank of the model, which this one's that's pretty darn good right there. I mean, for a 90s spam filter, just looking at the amount of words, that's known as the classification rate, also known as an A word, known as the... Did you want them in person? Oh, on Top Chat this whole time? It is called the accuracy of the model. That is called the accuracy. So the accuracy is the percent it predicts correct, which could also be found via the on diagonal. So you could add these, or you could take the complement of the misclassification. The accuracy. How accurate is it? Like, how accurately does it predict it? 93% of the time it's accurate in its prediction. Does that make sense, Kayla, to say 93% of the time the model accurately predicts what it is? So try to use it in sentences to practice and put an association in your head to say, oh, my model 93.13% of the time accurately predicts whether something is junk or safe. But that is how we would interpret that value right there. Along with otherwise identical word characteristics, do emails with higher frequencies of semicolons. So how about those semicolons? How do they impact whether an email is safe? So let's go to the semicolons right here. And semicolons are right here. So semicolons have a good to see you, Jameson. Semicolons have a what coefficient? So two otherwise identical emails, like they're everything word for word identical, it seems. But one of them has more semicolons than others. The email with more semicolons, positive coefficient, has a higher probability of safe. Those hackers haven't caught on to the semicolons yet. But two emails that are otherwise identical but differ in their semicolons, the email that has more semicolons is more likely to be safe. So semicolons, safe thing for emails, apparently, or more likely emails are going to be safe. Is the variable make statistically significant in the multiple regression model? Up near the top of the list, fit a simple logistic regression model predicting junk from make and verify that it's significant to full model. Which is it? Is there an association with probability of being safe in the word make or not? Oh my gosh, the longest question ever. Well, you don't need to answer anything here. You should be able to explain why this happens in a... Yeah, okay. I'm guessing make is not significant in this model. Where's make? Where is make? There it is. So make is not significant via the p-value. But what we could do is we can make a model where we just have make by itself. And make by itself, no capital. And with make by itself, we'll do make or model.make. Make by itself is statistically significant. But why is it not significant in the multiple world? So just by itself, like if we say like, can make help explain? Yeah. Emails that say the word make more often are less likely to be safe, lower the probability. We could even visualize this. But why in the multiple world is it not statistically significant? Why in the multiple world does it not do? Why? Over here in the multiple world, in this model, make is not statistically significant. It could be redundancy. That definitely could be it. And that's Lillian, great answer right there. That's kind of it because it was significant before. Like it probably has something to do with redundancy, and I think we can get VIFs on this. So let's look at some VIFs on that in multiple model. Variance inflation factor. There we go. Probably due to some redundancy, and here's the variance inflation. It's not that redundant. The most redundant thing is, or the one that shares the most redundancy is capital run length average with capital run. You notice these are kind of similar capital stuff. George is very redundant, or has redundancy among the others. But the variance inflation factor is telling us the amount of shared variation among the X's. And make has some redundancy, but not a ton. But it just doesn't bring with it enough new information. It doesn't help in a significant way with the other variables already in the model. So by itself, it's pretty cool. But when it's around a bunch of its friends, it's not. And what are we saying by its friends? We're saying when it's in the model with all the other X's, it just doesn't have what it takes with the other X's in the model. There's other X's. There's other better candidates that work better. .edu. Oh, see, that makes it a lot more likely to be like two emails that are otherwise identical but differ in their amount of .edu. The one with more .edu is more likely to be safe. And that kind of makes sense. It's like a school email, like probably safe. Probably, we hope. I got a spam from school email one time. So there's the make right there. Does the multiple logistic model provide a statistically valid description of how the probability of being safe varies with the predictors? Regardless of whether it's not, justify your answer with the goodness fit test and with the misclassification. So we did the misclassification rate earlier, but we just need to know this about the check regression. Yes or no in the chat. Does this model provide a reasonable reflection of reality right now? We can still use it either which way. It's not good if we answer this, though. It's not a good thing for the model. We can still use it, but does the model provide a reasonable reflection of reality? No. This is bad. No. We failed the check regression. You don't want the low p-values here. So this is not good. But model makes pretty good predictions. We did the predictions earlier on how to do the confusion matrix. I guess we did. We didn't show it, but we didn't write it on the code. But we did the mathematics right here for the misclassification rate and there it is right there. So that's the misclassification rate by adding up the off diagonal and dividing by the total, and then the complement of the misclassification rate is the accuracy. So, 93.13% accurate. Pretty good. Doesn't reflect reality. And nothing's perfect. That's seriously the way we talk. It's like, we tried. Interactions. Ooh, is going to get insane. Interactions right here may play an important role. Without interactions present, the model assumes that the curve is going to have a constant relationship, i.e. one variable will not impact the way another variable explains the y variable, the probabilities. So maybe what we did was too simplistic. Perhaps the probability of one variable depends on another. Fit a logistic model predicting junk from U and direct along with their interaction. Okay. Put that, there we go. And so now, oops, U-bot talking away right there. Oh, it's a lowercase u. So from U, good show, direct, and there we go. I've put a star right here to do their interaction. There we go. We go over our model as we always do. Change the limits on it to -15. We're going to have to change the xlim. So we're going to go to visualize model, and we're going to add in our model. We're going to go to xlim. Should pop up. No, guess it doesn't. Equals concatenate vector. There we go. You do. Oh, do we not? We don't. Do we? We don't. What command are you thinking of, Shreya? We do not have a U command. Okay. So let me ask you this. Is it good? And remember, we want safe emails. Is it good if an email says direct? Like, do you like emails that say direct a whole bunch of times? Do you like emails that say direct a whole bunch of times? Well, think about this. Look at the blue line. Look at the red line. So, direct, sometimes, what's the probability of being safe? Look at the black and the blue line. Sometimes direct, like the more times it says direct, sometimes what's the probability of being safe? Sometimes direct, due to the interaction. Sometimes what's the probability of being safe? Look at the black and blue line. Sometimes direct will blank the probability of it being safe. Sometimes, the more times it says it's direct, it'll blank the probability of it being safe. The answer is depends. The first one, yep. Sometimes it'll increase it, but sometimes it decreases it. So the way in which direct explains the probability of being safe depends on how often U is set. In instances where U is set a small amount of times, there is a very strong positive relationship where direct, if it doesn't say U that much, is going to increase the probability of it being safe. But in instances where U is set a large amount of times, maybe it's saying like direct to you, all this direct to you, and it's a lot of U and direct, like U is set a whole bunch and direct is set a whole bunch, then the probability of it being safe will be lower. So the way in which direct, once again, explains probability of safe depends on U. And that's the classic interpretation we use, where we say the way in which X1 explains Y depends on X2. This is the interaction right here, and you'll notice there's a different curve for direct depending on the level of the other variable, U. Does that make sense right there to say there is an interaction because the way in which direct explains probability of safe is not consistent, it's not constant. It doesn't have a constant sigmoidal up. The curve actually bends. If there's no interaction, I'll show the no interaction curve right here real quick. If there's no interaction, then the curve will have a same consistent, it'll be parallel to itself. So you notice right here now, it's always the emails that say direct more often that are more safe. And then it's always like for higher levels of U. But now with the interaction put on it, when we star this, which allows for the interaction term to be included in the model, we can see right here in the summary, we get the interaction term, and there it is. It's a negative interaction term, which means it's going to make it so it has a negative relationship eventually. Oh, no worries, Shreya. Good practice right here. Let me know if you have questions about this. Is the interaction statistically significant? Is it statistically significant? What are people's thoughts on is the interaction statistically significant? And take a look here or take a look here. I know it's a little different, but it is still the same conclusion. Yes, and this is doing the drop one right here. The drop one, we don't need it because it's just one level that we're dropping. It should be doing the top one with the chi-squared right there. And that should, there's the p-value. So that just confirms when you run visualize model, hint for your take home for the final. When you run your drop 1, it will do a partial F on your interaction if you have it in the model. So it is statistically significant. It does bring with it new information. That pretty good right there. For what value of direct does the relationship between change the steepest? So for what value of direct is it the steepest? So when you look at this curve right here, on what value of direct is U the steepest? Small, which I think overlaps medium. Is it small, medium, or large? Which value is it the steepest for direct with U? So just think of hills. Like you go out with your friend and you're like, wee, or you're like, wee. Large, right? So when you look at this right here, it's going to be the steepest hill for your friends to go down. Just think of sledding. So there's a stronger relationship with U and probability of safe for large values of direct. The reason you don't see the small is because there's an overlap in the 10th and 50th percentile of direct right here for values. The 10th and 50th percent overlap, so the black and red line are overlapping. Not fun, but it happens. Wish it kind of showed you that, but when an email does not have the word U in it, U is equal to 0, what types of emails are most likely to be safe? So U would be very, 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 very what right here? If U is not in an email, you would have a it'd have the what is possible value. So just think of words right here. Now we're on this graphic, but if U is in an email 0 times, what email would be most likely to be safe? Oh, I said, if U is in an email 0 times, it would have a very, very small value. Does that make sense? Because it's not in there. That's like the smallest possible. So you would want the value of direct to be very what? You're on the blue line now. If U is said 0 times, which is the smallest possible amount, you'd want direct to be what? Frankly, you'd want an email that just be a pointless email. But you'd want the email to have a what level of direct? So we're on the blue line because U is said 0 times, the smallest amount of times possible. You'd want it to have a very large value. Exactly. You'd want to be over here, like it said like 10 times. So if it said like 10 times, then it has a very high probability of being safe. So when U has a small value, then we would expect, or we'd want larger values of direct, more likely. Describe how the nature of the relationship between probability of being safe and frequency of direct changes as we consider the emails with the frequency of U. And we mentioned this earlier, that for larger values of U, direct actually goes to a negative relationship. So you'll notice right here, you get the sigmoidal down curve here. So really, what is the impact of direct? Well, it depends on U. So for high values of U, it actually becomes bad to see direct in there. So direct is good. Does it make sense, Kayla? Let me slow down. Because what we're saying here is, if an email, this is the previous one real quick, please let me know if you have questions. In the previous one, an email says U 0 times, which is the smallest possible value. That means we need to be over here on the blue line, and you'll notice direct is a good thing because it increases the probability of safe. But this is the next question we were talking about. For emails with larger values of U, well, then we would see that the amount of time it says direct is going to decrease the probability of it being safe. So what is the impact of direct? Well, it depends on how often U is said. For the earliest example, when U is said 0 times, well, that's the smallest value, then direct is going to increase the probability of it being safe in our algorithm. When U has large values, like it says, you should do this, you this. So the 0 question, because if U is said 0 times, it would have a small value. Does that make sense? Like, let me know if that makes sense. If U is said 0 times, U has a small value, because we're talking about how often it's said in the email. So if U is said 0 times, then that's the least amount of times it could be said, the smallest possible amount of times U is said. So with U being said 0 times, then direct being said more often would increase the probability. Awesome. And so we're on the blue line right now, which means this is the relationship we see between direct and probability of safe. So you'd be like, oh, it'd be good if it says direct now because it increases. Exactly. But in instances where U is said a whole bunch of time, like, you need to do this, you that, you that, you. Well, then if the email says you a whole bunch, then direct becomes a bad thing because direct is going to decrease the probability of safe. So if we say, is direct a good thing in an email? Well, that depends on the amount of you being said. If you is said 0 times, then direct actually makes it more likely to be safe. But yep, exactly. Awesome work. Kale, 100 points. Great practice. Keep asking those questions. Good work. That's what we talked about the initial relationship. Refit the model without the interaction. Visualize it. Notice how. Oh, weird. Oh. So this is without the interaction, which I already did. Let me go grab it. So refit the model without the interaction. No interaction. And with no interaction, all the S's are what to each other? Because it doesn't matter. It doesn't matter. With no interaction, all the S's would be what to each other? That's a weird. Whoa. Oh, I didn't do the XLM on it. All the S's are parallel. And we're expanding the view on it a little bit here so you can see kind of more of the S's of it. Once again, don't worry if you saw this on the previous assignment. It might look like you don't fit an S, but these are actually S's. It's just that you're zoomed in on a portion of them. So I've had people say, wait a minute, that's a line. That's all lines. And I say, well, zoom out a little bit and you'll see the S's. So it's just sometimes we're too zoomed in on a certain portion to really see the sigmoidal S shape of it. So we can do the X limbs argument right here to expand the X limits down here. You can just go crazy if you want and go like -100. Don't do this. I'm going to do it anyways, though. And they go like, whoa. Don't do that. But you can get different limits on it. The stronger the interaction, the more perpendicular, exactly. And there's no interaction right here. So since we have no interaction term, the lines, or the S's rather, are perfectly parallel. They're just like an S and S and S. So they're all perfectly parallel. Almost question on? Yeah, cool. Question number 2. That was a big question. Here we are with question number 2. Using the EX9 store data, this data set was created by a bank that was studying whether the association between shopping at stores at one store and others. Cool. It's real data. Fun. So the store names have been anonymized. Thank you. Fit a model predicting store 68, which levels are buy or no. So what will we be predicting here? Will we be predicting somebody buys or no? Which one of these will we be predicting? It says down there. You're welcome. Yeah, no, it's good practice. We need it. It's good practice. And I'm glad these videos get a lot of views. We will be predicting no. And it's confusing. We are predicting no because of the way the data is coded. So the data is coded as store 68, right? Store 68. Capital S. Where'd the data go? The reason we are predicting no, because no is what? In logistic, the level of interest is what? Like junk and safe right here. In logistic, the level of interest is what? In logistic, the level of interest is what? And so when you have buy and no, which is not no and yes, Shreya sees a great job. No is last alphabetically. Exactly. 100 points right there. Great work. No is last alphabetically. So in logistic, the level of interest is last. And don't worry, it's just good practice, and you'll see it when you make the model. So do we have any quantitative variables in this? Can I get a quantitative variable? Quantitative. No quantitative. That's going to be interesting. No good visualizations then. So there we go. Good stuff. Among shoppers with otherwise identical buying habits, they both shop at the same set of stores and not shopping at the other set of stores. Which one has the higher probability of buying at store 68? The one who buys at store 66 or the ones who do not buy at store 66? Are we just fitting a model? Fit a model from all others. Okay. So let's fit the model from all others. I know, right? So we're going to predict if somebody buys at store 68, tilde dot, data equals EX9 store, family equals binomial. Boop. There we go. And what do I care about now? We're going to look at that. So now among shoppers, we want store 68. from store 66. There we go. What's the only thing I care about here? What is the only thing I care about when it comes to that? The sign, right? Now this is going to be a little bit a lot. Let's write it down to make sure we see it. We are predicting someone does not purchase. That's because it's last alphabetically. Lauren, great to see you here. Yeah, awesome. 100 points, Lauren. Thank you for being here. We are predicting somebody does not purchase because it's last alphabetically. So we're predicting not purchase. Store 66 has a what variable right here for somebody. Be careful. I want an I word for it though. That's a what for store 66. It has a reference to compare it to. So that is a what word right there. Indicator. Great job, Shreya. Good practice. That's an indicator. So people who don't shop at 66 have a negative coefficient. Does that make sense? And that would mean between two people where one shops at store 66 and one does not shop at store 66, the people who do not shop at store 66 would be less likely to not purchase. That's a lot. So people who do not shop at 66 would be less likely to not purchase. Does that phrase make sense? Because that's tough right there to get out of this. People, why am I saying not? Because this right here, people who do not shop, because that's the indicator, at store 66, I'm saying less because the negative, and then not purchase because that's the what? Not purchase because it's the level of interest. Does that make sense? It decreases the level of interest. So I have my indicator here. People who do not shop at store 66. People who do not shop at store 66 would be less likely because negative coefficient. And then not purchase because not purchase is the level of interest we're talking about here. We're talking about related to less likely to not purchase. Now, if you reword this, references right, great job. Yep. Let's do a little rewording. They'd be more likely to purchase. Does that make sense? People who do not shop at store 66 would be more likely to purchase. Or we could say people who do shop at store 66 would be more likely, or we could say less likely. So there are the implications from this, and in much easier way to understand. So yeah, good to see you here, Lauren. It's tough to reword this and get it to the exact phrase, but that top is what the coefficients are going to tell us. We're looking at people who do not shop at store 66, that's implied right here, are less likely, implied right here, to not purchase because not purchase is level of interest. So when you think of this, less likely not purchase is easier said, more likely to. Do you get the flip right there from the line 209 to the next one? Nice job, Kayla. You've come an expert on this. You're getting it. Does that make sense as I go from less likely not purchase, more likely to purchase? Just that's all I changed going from that line to that line. I said, well, great job, Shreya. So now you could just change people who do not shop at store 66 are more likely to purchase. So people who do shop at 66 are less likely to purchase. Just because it's like, well, if they do purchase there, then they're less likely. If they don't purchase, they're more likely. So this is just a flip, changing the not with the more and the less right here. Because if you say the ones who don't shop there are more likely to purchase, then the ones who do shop there are less likely to purchase. But that's pretty tough. That's interpreting that coefficient is a lot of fun with all the knots and levels of interest and everything. But make sure to write it down. Even I was doing that to make sure I got it. I like exactly. You have to follow the sign right here when you have less likely, because that's the level of interest. We have to know what the level of interest is. This is the level of interest. We are predicting they do not purchase. We have less likely because the sign, and then we're talking about people who do not because we have the no right here. So follow what the output says, and that's a really good practice on interpreting. Confusion matrix. So we are evaluating how our model makes what right here. By a confusion matrix, I'm evaluating the what's of my model. With the confusion matrix, I'm evaluating the what of my model. Say, oh, well, we use this to look at how our model makes what's. Think of a P word. Prediction, Kayla, you got it. Let's start here by doing, my brain's gonna go, brain machine go brr. Let's start by doing the naive model. The naive model predicts the majority level for everything. So what does the naive model predict right now? The naive model would look at every single person we have and it would say, you know what? Maybe you got too many Word documents open. It says everybody's gonna what? Everybody's gonna what according to the naive, which is a very good place to start. When you make models, you first top out the naive usually. It's gonna say everybody would what? If you get output like this, you have to remember how to look for the naive. The naive's gonna what? Will it predict everyone buys? Will it say everyone's gonna buy? What will the naive predict? The naive uses the majority level. Trey, great work right there. No, don't worry. Do remember, like, the model predicts level of interest last, but when the naive says, I bet everyone's this, it's going to do it by the majority level of what things actually are. So you can look at it with the confusion matrix, table matrix. So we are predicting most people do not buy. So tell me, what is the accuracy of the naive model? And then we'll figure out the misclassification. So to try to compute this now, what is the accuracy of the naive model, also known as the classification rate? We're doing lots of great test questions right now, just practicing. If you've been here, this is just a huge review session for, Shreya, great work. That's the accuracy of the naive. So Shreya, what can you do instantaneously? And you'll know you have it. That's the accuracy. No, you got a majority level. Say most people are this. So Kale, if you're in your house and you're predicting whether someone is your child, what would you predict for everyone in your house? Just normal day on your house. You walk into your house and you see someone. What would be your naive model for them being a child? Would it be that they're a child or they're not your child? Like when it just comes to like, you've got, your kids, your husband. Just thought of a funny example here. Just say to your husband, you're using this model from now on. Just be like, you're my child. And you're like, what? And you'd be like, oh, don't worry. You're just a misclassification according to the naive model. So why would that work right there? They're all your kids, everybody, because most of them are your kids, right? Including your husband is the misclassification with the naive model. So, and then the accuracy would be the children properly classified as children. So you say, well, most people in this house are my kids, so everybody's my kid. That's how the naive model works. It just works off a majority level. But you could use age properly to properly classify because age has a very strong, I'm assuming, relationship with classification of children. So my brain. So this is, I think Shreya's already done it. Thank you, Shreya, right there. Finding the probability. And so now the misclassification of the naive is 61 point. That is how it really feels. You're welcome. I'm just a big kid anyways. There's the misclassification rate. Here's the classification rate. And there, great job, Shreya, right there. Excellent practice. And that's the naive model. Now, when we look at our model is the inside of this. And we have what is called the on diagonal because it matches up with things that are accurately predicted. And we have what is called the off diagonal. If you calculate the misclassification rate, you can get the other one as quickly by doing the complement. Woo! This doesn't look good. I don't like how those numbers look because that's the misclassification. And not gonna. What? That's why we do things in our head. 24. Not as good as I would like. We're on to 25. The naive model had a misclassification rate over here. The naive had a misclassification. Sure. It's got 2 eyes now. It's got no eyes. It can't decide. There we go. Nice job. The naive had a misclassification of 31.33. I'm probably blocking it. I am. Overall, our model does a bit better than the naive. I would prefer my model do a good bit better. The model gets a 75% accuracy versus 25% misclassification. Not too great. And if I'm to say what we would be doing next right here, we'd be asking, is this model a reasonable reflection of reality? And the answer is, this model, ooh, is this model a reasonable reflection of reality? Yep, 25% misclassification, about 24 point something. Is this model a reasonable, yes or no, is our model a reasonable reflection of reality? With check regression, check the arrow, because the null hypothesis is, hey, it's a good model. That S is a good shape. Brian's handwriting's pretty bad. So the null is that the S is a good shape. And the alternative is that the S is a bad shape. If we tried to fit this is an S. I know it doesn't look like it. It's just, it didn't fit very well. So if we tried to fit the S where it doesn't belong, the check regression is going to come back with a p-value like this, which means we say reject the null. We have evidence that the S is not a good shape. So even though we didn't get as good of a model this time, not as practically significant of a model, don't worry, we don't want statistical significance here because that means we have evidence of a problem. Our model is like, hey, it's an all right fit. It's doing okay. But then we have to ask, is it useful via the confusion matrix on how it predicts? And not as useful as the last one, which was a bad fit. There's the check regression. Third question. Here we go. Time for the last question of the night. Question number 3. And please keep those questions coming in. Great work here, everybody. Question 3. Download and import the Act11 account.dat using the following. Strings as factors means we're reading in strings, which are words, and we're going to put them into categorical variables, calling it account. Do all this fun stuff right here. Account, save into, and make sure you have the file downloaded. And Shreya, 100 points. This is what you were talking about earlier, where someone might not have the file stored. If you do not have the file stored, you will get an error like that telling you that file is not in your current working directory. Now, you might have the wrong working directory set. Yeah, Shreya's like, I've seen that right there. I know that error. 100 points, because I've seen this error a lot too. So at this point, you're reading a file on your computer. That's what the read does. I do want to point out, a lot of times people have told me after they finish the class, well, Brian, I have an Excel file. Well, we can use what's called read Excel and take a wild guess at what the read Excel package does. Does anyone have any crazy guess? And it will, Lillian, good point right there. It will change the file name with more extensions if you download it multiple times. What do you think read Excel does? Which we're not using read Excel here, but what do you think read Excel does? The package, the library, read Excel. Just take a wild guess at what it does, or the library write Excel. Just take a wild guess. Oh my gosh. It reads Excel files. It reads Excel. It reads them. Like, you can read an Excel file into R, or you could write an Excel file. So I could go right here and go to write Excel. There it is, write Excel. I could take account and say account.xlsx. And guess what? I'm going to go right here, blank the screen, go to account.xlsx. Where? Not there. Account. There it is. And now, make sure it loads up. I just took that file you saw in Jump or R, and I just wrote it to an Excel file. So that file I've loaded in, if someone's like, hey, I've got my data in R and I want to bring it to Excel, I say, oh, just write the file. So it's kind of like a save as, but we don't, because someone had to create a package here to take your data frame and then just simply write it. And all you have to do is say, what do you want to write? So the function here is, what do you want to write? And then what do you want to write it as? And then if you have a file like that, you could just go here to read Excel, because now I've created that file. And and now I could just say read in this file, because I created it, and it would read it in for me as an Excel file. That's just a bunch of like documentation on it. So it would read in the Tibble file right there. So it saves them as a Tibble? Didn't know that. That's besides the point. But those are really nice packages that do a lot of helpful things. Okay, so we need to fit, oh no, got the wrong file name. That's a dat file, .data file. We are predicting, okay, fit a model predicting if someone purchases from those, purchase from these variables. So don't put them out of order. M save into GLM, purchase from checking balance and branch bank. No interaction. When we say no interaction, you're just going to add the variables right here. Add. And then data equals. I like to do a space to start a new line. There we go. Thank you. And then family equals autocomplete is your best friend. It'll keep you from all your typos. And there we go with binomial. That actually works. I'm just not a fan of it if you do the parentheses because it seems more like a function than telling it what to do. So now it says to fit the model, use the drop one. Well, let's visualize. Usually I like to visualize. I like to see what I've created. And here, whoa, pretty. Do we get to do interactions? Oh, yes. Pretty. Let's go loc. Loc changes the location of the output there. And there you go. There's your pretty model. Let's go here and go to xlim equals concatenate negative 50,000. Oh, don't do that. And to 300,000. There we go. Look at that. We could probably zoom in a little more on this portion to the 100,000 mark. So let's do that. There we go. Neat. That is a logistic model with a lot of indicator variables because the variable branch bank has a ridiculous amount of levels. So if we go here and look at account and go to branch bank on it, that has tons of categorical levels. So how could we figure out, and the quickest way is to do this, how could we figure out whether the branch bank is statistically significant? So we're looking here at checking balance has a positive relationship with somebody purchasing, and branch bank also has a relationship here. But how could we see if branch bank itself, and there's the answer, how could we see if branch bank is statistically significant? Because the output for it hints to the take home again. The output for it's going to show all these different levels right here. The drop one, exactly. You see how it has all these different levels, which are differences from the reference level. Like, oh, is this one significant? Well, it's significantly different from the reference, which is probably 1. Yeah, it's branch bank B1. We don't see it because it's first, alphabetical. Remember, reference is first, logistic is last. And so we can do the effects test with the drop one. And the thing is, Rock knows... It doesn't matter! Rock, why does it not matter? Who can explain why I don't really have to do this right now? I mean, I should. This is good statistics. But why does this right here not matter? And I want you to see why you can do it a lot quicker if you know this. And we get a little better decimal accuracy. Oh, no, but it is 3 or more. It is 3 or more levels. It's a lot of levels. It's like 20 levels. So we do have to do it. But I didn't mean it didn't matter like we don't have to do it. I mean, we've already done it. Because when you visualize the model, and this is a great thing to know, if you visualize, like literally hints to the take home, a lot of people get stuck on this. If you visualize it, what did it just do for me? Look at the output down there. What did it tell me? What's it doing for me? Which we did ourselves. We ran right here the effects test using the drop one and got the p-value of this, but we didn't have to, and we already done it. Right here. Now, this is not as decimal accurate. This is showing more decimals. It's just that this rounded it to e to the negative 16. And this is telling us, yeah, it's ridiculously significant. Like, this is ridiculous, and this is ridiculously significant. And it tells us that that really helps. Those different levels to branch bank, which is a categorical variable, creating different sigmoidal S shapes, is super helpful. But here's the cool thing. The graphic gets to look even a little better than this. Because now, all those, because there's no interaction, all of those are what to each other. Every single one of those is what to each other. We could do it right up here. Every single one of those S's is what to each other because there's no interaction currently. Every single one of those S's is what to each other. They're all what? Because there's no interaction. They're all parallel. So it's always, whatever bank that is the highest probability of somebody making a purchase in whatever bank this is, which have the most negative coefficient. This goes to your homework assignment. The most negative coefficient is going to be, I believe the most negative. Oh, I already made the model. Okay, 2 seconds. We'll figure it out. I want to see it before I do it. I don't like scientific notation that much. There we go. Let me go. I'm going to find out the exact answer. I'm going to order my output. Let's coefficients. There we go. Here we go. Oh, let's just do this. This is nice. DF. There we go. Cool. The most negative is bank 14. So, and probably if we bring back the visualization, you'll see that that's the purple one right there. So if we bring back the visualization on it, that is bank 14. Should be. Oh. And very hard to see, but that is bank 14 right there. Does that make sense? That would be very hard to see. But I figured out it's bank 14 because it's the most negative. Does that make sense? So I know I saved everything as a data frame. We don't expect you to go that in depth, but I can see that bank 14 has the most negative coefficient, making it this right here. Now, the one with the most positive coefficient is going to be bank 10, bank B10. So that's the red line, which is super hard to see. You can see it right there. You can see the red line, bank B10 is that one right there, which is the highest, and you can just barely see it. So this goes to your current assignment, predicting which one has the most likely. So people at bank B10 would have the most likely probability of purchasing, where people at bank B14 would, branch 14, have the least likely probability of purchasing. And you could say they're less likely than people at branch 1 because that's the reference level, which is the black line. I got extra black lines here, but the reference level is where the black line starts. Hey, Benton, great to see you here. We're towards the end, but let us know if you have any questions. Just looking at tons of output and trying to make sure we see it. And I think Shreya was pointing out here that if we include the interaction, which we're just going to change this to a star right here, then the lines are no longer parallel. Is the interaction statistically significant? Does it bring with it new information? If you notice, no longer for all the banks does checking balance have a positive relationship. Some of the banks have a very strong positive relationship. Some of the banks, whatever bank this is, has a negative relationship with purchasing. Some of them have weaker relationships. That one is a very weak one too. So you notice with the interaction term, the relationship right here is not constant. And as Kayla's pointing out, the interaction is statistically significant. And we could also just do the drop one also. Where's my drop one code? Drop one. I'll write it again. Drop one for our model. Test equals. And look, the p-value. What do you notice the p-value is as with the visualized model? And that confirms it. Good place to end on it too. What do you notice the p-value of doing the drop one is for when you do the visualized model for checking to see the overall impact of the interaction term? It says the effect of the interaction term is statistically significant, as in the interaction term brings with it new information. And you can see it right there. It did some drastic changes to our model. They're the same exactly. And we should look at how well does this new model predict. So let's go here to our confusion matrix. And it gets right. The accuracy of this, the accuracy of this model is, that's the miss of the model. Model might not do that well. Model predicts 66% accurate correctly, and the naive model, whoo! Why is our model garbage? Why is our model? Is it a reasonable reflection of reality even? Why is our model like, or you could say maybe this is helpful. Maybe, maybe it's the stock market here. Our model gets right 66%. The naive model gets right 65%. Our model doesn't even do 1% better than the naive. Our model does basically the same as the naive. And the naive would predict what for everybody? The naive would predict what? Think of majority level. The naive would predict what for everybody? Kind of a good review of what we've been doing. The naive would predict everybody what's. The naive predicts every single person what's. It says no one purchases. And this... How's our... Ooh, look at that check regression running. Whoa. How are our friends doing? Are our friends fighting? One friend's like, eh, and the other friend's like, no. That's cool. I've really never seen them this far apart. This friend says, yeah, use that model. And the other friend says, no, don't. They don't agree at all. And here's the thing. This model, as cool as it looks, and as fun as these lines look, this is our worst model of the night. We got friends fighting about we should use it, we shouldn't use it. We've got a predictive capability of the model that's super close to the naive to be like, just no one purchases. Let's just go with that. So overall, all as great as this model looked, as fun as all the lines looked, this is by far the worst model via the evaluation criteria that we have to say our friends are in disagreement, our naive and our confusion matrix are turning out the same. Yeah. I like that the two friends, like you got two friends. You want them to agree usually, but today they're fighting. Well, I want to say a huge thank you. Let me throw out 1,000 points if you've been here. Great work. I know it's later in the evening. It's almost 9 for you. I might make some fries, or I don't even know what I'm going to make for dinner. You're welcome. Dinner time. Go eat. Go relax. Hang out with family, friends. I'm going to do the same. Thank you so much, everyone, for being here. It's going to be Friday. Friday here soon enough. Bye for now, everyone. Bye. Elevator music. Sad music for everyone. Not sad, but cute.